Hello everyone. I want to start off this video, which is going to be on measurement, uncertainty, and significant figures. I'm going to start off this video with talking to you a little bit about how things are measured and how every time you make a measurement, you're actually going to include some uncertainty in it, and then how are we going to deal with that uncertainty. So let me start off by sharing my screen to show you some very specific photos. So what we have here is a little binder clip that I put next to a ruler, and it's not that good of a quality ruler. The important thing is it's actually kind of nice because the zero doesn't actually start on the end of the ruler. You'll find out that when the zero is on the end of the ruler can get mauled quite a bit, and then that introduces an uncertainty or error in the measurement to begin with. But in all reality, it doesn't matter. No matter how perfect your instrument is, no matter how perfectly shaped your object is, you're always going to have some uncertainty in the measurement. For instance, if you were to zoom in with a microscope really close to the edge of that seemingly perfectly straight edge, you would actually see it's quite bumpy at the microscopic level. And if you go far enough to where you're starting to interact with atoms and molecules, you'll see that there's some fraction of atoms and molecules that are a significant distance away from the majority of the atoms and molecules. So even defining where the edge would be is kind of difficult. But one thing I wanted to point out for you is it's kind of hard to tell here, but this is actually set up ideally. I actually made sure I put the binder clip, the purple object, I made sure I put that, lined it up perfectly on the zero on the left-hand side of the yellow ruler. And then I took the photograph so that I looked straight down perpendicular to the page and therefore perpendicular to the edge of the binder clip so that I wouldn't get any what's called parallax, because in principle, if I lean too far to the left, then notice it looks like the measurement way out here is 2.5 or 2.4 something, 2.3 something maybe. Or if I went too far to the right, I actually might think the measurement's more like 2.41 or something like that. So you could get a whole range of measurements by not lining your head up properly. So what you normally want to do is try to make sure you get the left hand set up perfectly, right in line with the center of the line, or if you choose, you can actually do the left edge of the line and then read everything else from there on out to the left edge of a line. But once you have the left edge set up on the zero mark, then you want to make sure you're looking perpendicular to the page to see this, and that way you'll rule out any kind of parallax, which is just built-in error basically. So in this case, what I want you to see is from 0 to 1, there are actually 10 spaces. I'm counting spaces, not lines. That's important to understand. I'm counting spaces, not lines. So the first thing you want to do when you grab a ruler is you first want to find the 0. You second want to find out how many spaces are between 0 and 1, or between 1 and 2, or 12 and 13, or whatever. Just one unit, how many spaces are there, so you'll know what those spaces mean. Since there's 10 spaces between 0 and 1, each one means that's a tenth of 1, so it's 0.1. So if you were to try to count these numbers, the leftmost number would be 0, 0.1, 0.2, 0.3, 0.4, 0.5. Notice the 5 is a little bit longer. That's normal with rulers and meter sticks. And then 0.6, 0.7, 0.8, 0.9, and then 1.0. Okay, so that's one thing you want to do. Now, when I look at this, and I assume that I did get all the parallax out, it appears to me that this object has a measurement that's slightly bigger than 2.5, but not quite to the 2.6 mark. Again, you're starting at 2, and you'd be 2.1, 2.2, 2.3, 2.4. Then the big one's 2.5. Notice it does appear to be a little bit past that, but definitely not far enough to call it to the 2.6 mark. So I'm going to call this 2.5 something, and this is the key point. Notice the smallest marks on this meter stick are 1 decimal place, the 0.1 marks, for instance. We always, unless it's of course a digital device, we always measure to 1 decimal place beyond what the measurement has, because we can certainly tell the difference between, let's say, 2.51 and 2.59. Maybe I can't tell the difference between 2.59 and 2.58, but I certainly can tell the difference between 2.51 and 2.59. I would say I could probably tell the difference between 2.51 and 2.53. So that would suggest that the uncertainty is probably 0.02 centimeters. Okay, so that's the things you want to think about when you're measuring, is how precisely you can measure it. In this case, I'm going to call this measurement 2.52. So this would be 2.52 centimeters. And notice I did carry it to 2 decimal places, even though the marks only go to 1 decimal place. That's key when you're using meter sticks and triple beam balances for mass and stuff like that. Now, to avoid this whole parallax issue, they made ways of avoiding it, and one of them is the mirrored scale. So this is a galvanometer that we have at school, and with that galvanometer, if you look at it from the side, then you'll see 2 needles, 1 needle in the mirror, and then 1 needle that's the actual needle. So one's the actual reflection. But as you move closer and closer to being perpendicular to the surface, these 2 needles, the image and the real one, come together, and you end up getting 0 parallax when they're lined up. That's what a mirrored scale is used for. Then you can actually know for certain that you're not being messed up in your measurement by parallax angle. So that's something to keep in mind. Another thing is the uncertainty. I told you a second ago was I wasn't that confident in my ability to discern the difference between 2.1 and 2.51 and 2.53. So in that case, my uncertainty would probably be about 0.01. In other words, the whole range would be 0.02, but I think I'm pretty close to within 0.01. So I would call that number that I measured for the binder clip 2.51 plus or minus 0.01. Okay, and that's normally what it is. That last digit that you put to the right is the one that has a little uncertainty in it, and a bare minimum is that the uncertainty is going to be plus or minus 1 in that last digit. In a case like this, let's assume everything's actually lined up and parallax isn't an issue. It looks like it's you actually look like the left-hand side's not lined up. That's okay. What I'm trying to point out here is when you got curved objects like this, it's a little bit harder to estimate exactly where that is. So maybe this object would be, let's assume that this is actually not shifted over, and I was just reading this edge. I would assume this is roughly 4.4, and I'd probably say either 4.45 or 4.40. In other words, my uncertainty in this is at least 2 or 3 in the last decimal place. So that's another thing to keep in mind when you're actually making measurements, is how easy is it to measure. It could be a problem that is just your ability to get the equipment you need, whether you need some vernier calipers or something like that, or it could just be a matter of the object's not ideally shaped to be measured. All of those are fair game, and you use those to try to gauge the uncertainty in your measurement. The key point, though, once you figure out these uncertainties in your measurement, you can never have more than one doubtful digit or one uncertain digit. So that's where you have to round the number to. So if the 0.0, if I call this measurement 4.45, the 5 is the doubtful digit. And instead of saying plus or minus 0.01, I'd probably say 4.45 plus or minus 0.03. So that's something else to keep in mind. Also, when you want to talk about measurements, you want to keep in mind what you're measuring with. So this is a passcode product that's sold. We have a couple of them, and we have this one as well as some wooden ones. But the neat thing about this is one side of the meter stick is actually measured in decimeters. So this is 1/10 of a meter. So if I put an object up there, I think it would be pretty obvious that if I put an object that extended from this edge all the way to right about here, you would not call that 1. You would say its length is maybe 1.3. So notice in this case, you are actually trying to estimate what value 1 decimal place is, even though it's only marked to the whole number. So this would be 1.3 decimeters. When you do it with this guy, let's say it came from 0 all the way to right about here, then maybe you'd call this 11 point, notice it only goes in halves, so these are only halves. So I'd say maybe 11.75, something like that. That's a kind of weird one because it looks like it's dead center between halves, but because I used a half measurement, it's easier to work in quarters. So that's why I said 3/4 basically. But when you go to this, which is the same scale we were on before, where the smallest one is 1/10 of a centimeter, i.e. it's a millimeter, then of course you do 2 decimal places, just like you did here, but the 2 was a little weird there. So those are some things you got to keep in mind. So when you do have these measurements, the next thing you got to do is you've got to be able to do science with them. You've got to be able to make calculations. For instance, the length, width, and height of a block of wood isn't going to be any good to you if you're wanting to calculate its density. But once you use the length, height, and width to calculate its volume, then you have its as volume, and if you divide the mass by that, you could actually determine its density. Therefore, you've managed to do some calculations to get the density, but you took a number that was uncertain, a length, another number that was uncertain, a width, another uncertain number, the height, multiplied them. What are you supposed to do? How many digits are you supposed to keep? That sort of thing. So we're going to give you a way of doing that fairly efficiently, but sometimes erroneously. But in doing that, we also need to talk about what are these units of measurement that we're using. So it turns out the system of units that we like to use in science is something called the System International, or the international system. It's what we used to call the metric system. So basically, it's a system that's oddly based on what's used in Great Britain, which is what we call now our system, the system that we use here in America. Us and one other really, really small country still uses the system of units, and the system of units we use is called the British system. So the British system has the feet as a unit of length, the second as a unit of time, and it actually uses a weight, which is a force, as opposed to the mass. So it's basically a foot, second, pound system. Whereas in science, we use the quote unquote metric system, but we really use the international system. And the international system is called the MKS system. So meters for the length, kilograms for the mass, and second for the time. You can build on a lot of units with those 3 base units, but we'll learn later that that doesn't cover some of them. For instance, it doesn't cover temperature, and it doesn't cover brightness of light and stuff like that. Well, it sort of covers brightness of light, but anyways, we'll work with some of those as the course goes on. But right now, I need you to understand that with that MKS system comes a very distinct definition of a meter, and a very distinct definition of a kilogram, and a very distinct definition of a second. So for a long time, we used the definition of a second to be 1/86,400th of a day. So you could just basically determine how long it took the sun to appear at the exact same latitude in the sky, sort of, over the same latitude in the sky. And the time period between those would be 1 whole day. So you divide that time period by 86,400, and that would give you the unit of 1 second. And everybody could measure that. That would be great. Yay, yay, yay. Well, turns out our Earth is actually doing some funny things. Specifically, the moon is slowly drifting away from us. And by slowly drifting away from us, that actually is causing different forces to speed up, or in our case, to speed up the Earth or slow down the Earth, that sort of thing. So there's some problems with that. Ultimately, what we've decided on was that the unit of time will actually be measured by cesium-137. That's a radioactive isotope of cesium. And it turns out that this isotope of cesium has this metastable reaction that occurs quite frequently on a human time scale, but on a microscopic time scale, it's very, very slow. So what was decided to do, that we do for a unit of the second is we take this oscillations, this nuclear particle dropping from one energy state to another energy state and giving off a photon of light or some other kind of particles. We'd count that occurrence, and once we got up to 9,192,631,770, that would be exactly 1 second. And since it's a random function and it's billions of them occurring, we know that's very stable. And in fact, we can be certain of that time period up to like 9 or 10 decimal places. So it's a really, really very precise way of measuring time. So that's how we measure time. So everybody can get a sample of cesium-137. Every country on Earth, every alien species we meet could get a copy of or get a sample of cesium-137, measure this, and we'd all agree what a second is. Now, what about distance? Well, the distance used to be measured. You probably heard the foot, and it would be the foot of the emperor. But how many people got to see the emperor and all this sort of stuff? So there's a little bit of problems with that. Then they took the equatorial distance of the Earth and divided it by a certain number. Blah blah blah. All those things have different problems, of course. But ultimately, what we try to do is try to get it where it's not dependent on some physical object, but rather something that everybody can measure. So at the end of the day, what we ended up doing was deciding that the distance that light could travel in 1/299,792,458th of a second is the distance called 1 meter. So in other words, now the speed of light is defined definitively with an infinite number of decimal places to 299,792,458 meters per second. So by doing that, we were actually able to define a meter as a concept as opposed to a physical object. Now we're still working on a way to make the mass a concept or something that everybody could measure without hinging on a particular object. We haven't gotten there yet, but we are getting closer every day. Currently what we use is a platinum iridium cylinder. The platinum iridium cylinder is the unit of kilograms. So basically its mass is 1 kilogram, which if you measure that at sea level, that's about 2.2 pounds. But it's basically a sample of platinum and iridium that's been designed or shaped in such a way that it has a minimal amount of surface area. Those of you taking calculus-based physics can do some neat little derivatives and show that that has a very unique geometry to it to have a minimum of surface area. And that's the way they designed this thing. I'm going to show you a picture of it. And here's the picture. So this is an actual replica of it, and what they have is a platinum iridium cylinder. And if I remember correctly, the height is 2 times the radius. That's sort of what makes it ultimately have a minimal surface area. And the reason why you want to have a minimal surface area is the same reason you make it out of platinum iridium. It's the one thing that's the one way that's easiest to avoid contamination. The more surface area it has, the more easy it is to contaminate. If we put some other metals on there as opposed to platinum iridium, it'd be more likely to interact with other things and make compounds and change its mass and all that stuff. And then they store it inside of a double bell jar. So basically this bell jar has been more or less in a vacuum situation. And then outside of that's another bell jar that's created another vacuum. So it keeps dust from getting on it, and they break it out about once a year. People can make replicas of it. And then other countries can have their own replicas. So I did get this photo from someone, so I should actually show you the citation for that. And that citation is right here. So it's going to show you any minute now. So that's where I got the actual photo. And now I'm legally finished with dealing with that. I'm going to stop sharing again. So now we have an idea that measurements do have uncertainty, that they're based on some standard that everybody should be able to agree on. And now we're going to deal with how that uncertainty propagates. So one of the things you might think of when you go to, I'm going to switch cameras now. I'm going to switch to my document camera. When you go to make a measurement, you might think, well, what's going to happen if I let's say multiply 2 numbers. Let's say we multiply the number 6.2 feet. I know I'm jumping right into using a unit other than our MKS system. 6.2 feet. Let me do this, hold on. Sometimes it takes a word to be in the field of view for it to 1 second. There you go, that looks a little better. So let's say we have 6.2 feet by 7 feet. And we've measured the 7 feet to 2 decimal places. We've measured the 6.2 feet to 1 decimal place. When we actually multiply that, we'll get 43.4 feet squared. We'll talk about that feet squared thing later, but that is a very important aspect. You don't just throw off units and ignore units. In fact, you can't add 2 numbers or subtract 1 number from another unless they have exactly the same units. And when you multiply the units, you get a product of the actual units that comes out. Similarly, if you divide 2 numbers with units, denominate numbers is what they call them, then you'll get a division of the 2 units as the resulting unit. What this says, though, it says that basically there's an error of plus or minus 1 in this measurement. Plus or minus 0.1 feet. And then it also says that 7.00 is plus or minus 0.01 feet, bare minimum. If they don't take the time to tell you, then you can assume it's 1 in the last decimal place. 1 in the last decimal, or excuse me, 1 in the last decimal place. Sometimes, like I showed you earlier, sometimes you might want to call it 2 or 3 in there, and you need to actually specify 6.2 plus or minus 0.3. Sometimes people put the foot there and there, doesn't really matter. I guess technically speaking, you should put parentheses around it if I keep all the units on the outside, just to keep from confusion. But that's really what that answer is telling us. But if you were to actually consider, what if I allowed this to go up 1, then I had 6.3 feet multiplied by 7.00 feet. Well, that answer would give me 44.1 feet squared. And similarly, what if instead of changing this one by 1 of its error units, what if we change this one by 1 of its error units? So let's say 6.2 feet times 7.01 feet. And when we multiply that, we get 43.5 feet squared. And I think what you see from that is we go from 43.4, 43.5 to 44.1 with these. So we expect that the uncertainty in this should actually be in the second digit, because we went from 43 to 44 to 43, so on and so forth. So that gives us an idea. And in fact, the rule that we're going to use is called a significant digit rule. So basically, significant digits are all the digits that are used to tell you information about the number, not the digits that are used to just put it in its right size. Okay, so the easiest way I found to help people understand that is make up these very simple rules. Rule number 1, the MSD. Okay, that to me means the most significant digit, most significant digit. By most, I mean it's the leftmost. Remember, this is the 10th place, for instance, and next would be the hundreds place. This would be the, the ones place, the tens place, the hundreds place. This would be the 10th place, the 100th, THS place, the thousandth, so on and so forth. So when I say most, I mean the one with the highest ranking. So in this 6.3 case, the most significant digit would be 6. So the MSD is the leftmost non-zero number. That's rule number 1. The MSD is the leftmost non-zero number. Number 2, if there is a decimal present, then the rightmost digit is the LSD, the least significant digit. Okay, so MSD means most significant digit, LSD means least significant digit. 3, if there is no decimal shown, then the rightmost non-zero digit is the LSD. And then finally, for the MSD, LSD, and all digits between, are significant. Okay, so that's your rules. So for instance, if I write 5.07, that has 3 significant digits, or 3 sig figs, that's another way to say it, because this is my MSD. There's a decimal present, so this is my LSD, and it wouldn't have mattered anyways because that digit's non-zero. Whereas if I did 5.000000, then my MSD is this guy. And then I go to the rule that if there is a decimal present, there is a decimal present. So the rightmost digit is the LSD. So there's your LSD. And then rule 4 says that one and that one, 1, 2, and everything in between, 3, 4, 5, 6, 7. So there's 7 significant digits are sig figs in this number. A common problem that you run into with this scenario is your book will inevitably write the number 5,000. Okay. Technically speaking, that number 5,000, since it doesn't have a decimal present, this number is your MSD, and then this number is also your LSD, so it has 1 sig fig. But your book is inevitably going to call that 4 significant figures. Okay. The way you actually avoid this problem is you're never supposed to write, if your last number is 0, you should not write it that way. You're going to either write it as 5,000 and take time to be pedantic and put that little dot on the end, which is going to be confused for a period too, and that could be a whole other problem. Or the better thing is actually use something called scientific notation, in which case you'd write it as 5.000 times 10 to the third. And then there's no ambiguity. Everybody knows a decimal is present, so this is your LSD, and this is your MSD. So this one would actually have 4 sig figs, and this one would also have 4 sig figs. Okay, so your LSD is this, your MSD is that. Because there's a decimal present, that's how we knew that was the LSD. So that's a good way of doing that, of figuring out how many sig figs there are. Just be advised when you use your book, if it gives you a number like 100 or 500 or 1,000 or 10,000, you're going to assume all those, at least for the problem that they're solving, you're going to assume all those zeros are significant, even though they're breaking the rules. Okay. You might want to talk with your individual instructor if they're doing something different, though. Now back to this number, what we see is this has 2 sig figs, and this has 3 sig figs. So according to the significant digit rule, whenever you multiply or divide two numbers, you have to round your answer to the number of sig figs that the number with the least had. So the number with the least was 6.3, or 6.2 is what we originally started as. So that had 2 sig figs. That means our answer needs to be rounded to 2 sig figs, which is the same thing we discovered here. We just discovered that the digit that was changing was right here. It went from 3 to 4 and then back to 3 again. So by using that, we realized, oh, it should be rounded here because that's clearly a doubtful digit. So we would end up rounding this to, from that original number, 43.4, we would call that 43 square feet. And that would be the proper significant digit rule. So the new rule we learned was multiplying and dividing. Answer should have the same number of sig figs. Notice I'm flipping back and forth between using significant digits and significant figures and sig figs. I want you to get used to that. So the answer should have the same number of sig figs as the number used that had the least. I know that's an ugly sentence, but you should be able to understand it given the context that had the least or fewest sig figs. So if you're dividing one number by another and one number has, say the numerator has 15 sig figs and the denominator has 3, you're going to have to round the answer to 3 sig figs. Similarly, if you multiply two numbers, one has 34 sig figs and the other one has 2, then you're going to have to round your answer to 2 sig figs. But what about when you actually are adding two numbers, say? What do you do then? Let's say we're adding 4.371, and at the same time, we're going to add that to 302.5. Now, in a calculator, this number right here, 302.500, is identical to 302.5. Right? If I put this in without the zeros and then do minus and put it in with the zeros, the calculator will tell me the answer is 0. Because mathematically they're the same, but in science they're very different. You know, this might cost you maybe 1,000 to 10,000% more money to get something, let's say, created to this precision. So 2 extra decimal places could cost a lot of money. You wouldn't want to not report them just because, you know, it's a pain to write numbers. So what do you actually do when you add them? Well, when you add them, you go ahead and just keep track of what's supposed to be there and what's not. So these two are really, since this is a doubtful digit, remember your rightmost digit's always uncertain or doubtful. So that digit's uncertain and this digit's uncertain. And these are, there's no hope to know them, but we're going to pretend like they're 0. So I do 1 plus 0, I get 1. I do 7 plus 0, I get 7. I do 3 plus 5, I get 8. I get 4 plus 2, I get 6. I do 0 plus 0, I get 0, and then 3. So what you can see is clearly this was a doubtful digit with a complete unknown, so that's like doubly doubtful. This was a known digit, but this one's completely unknown, so that's really unknown. And this one's a good number, but this one's doubtful, so that one's doubtful as well. So in this case, we're going to have to say you're only allowed one doubtful digit. So we're going to have to call this answer 306.9. Notice you I rounded up because this digit was 5 or larger. Some textbooks, some authors, some instructors use a different rule because you can tell you're not really dividing the numbers up evenly. Like for instance, 1, 2, 3, and 4 as a digit here, or 0, 1, 2, 3, and 4 as a digit here, all get this made into 306.8. But here you got 5, 6, 7, 8, 9. And to sort of take that into account, they can do things like count what this digit is, or excuse me, count whether this digit's odd or even, that sort of stuff. I usually don't mess with that. I just always round up if this digit is 5 or larger, and I truncate, that is, just erase it if the number is 0, 1, 2, 3, or 4. So if it's 306.80, 306.81, 306.82, 306.83, or 306.84, it's going to become just 306.8. All the other ones is going to become 306.9. So as I said before, numbers matter, but also digits. These were digitless numbers. They're non-denominate numbers. So that's why I didn't include a digit, but you always want to think in your labs and in your class, hey, I just drew a number. Does that have a unit? And let me make sure I get that unit right. Two numbers, I already told you, cannot be added unless they have the same units. Same thing with subtraction. But multiplying, you can multiply anything by anything or divide anything by anything digit-wise. You just have to make sure you keep the units in line. So those are our significant digit rules. There is a problem, though, and remember I told you this was a approximation. This is an approximate way to actually figure out how the errors propagate when you multiply two numbers. Let me show you a problem. Let's take, for instance, the number 1.09 multiplied, and let's say that's in meters, by the way, multiplied by 0.99 square meters. Okay. When I multiply those two numbers, I get 1.0791, and that's meters times meters squared, so that becomes meters cubed. I'm just doing that to have a unit on there so you can see how numbers normally have units. When I do this, I haven't done any significant digit rules, but the significant digit rules would tell us, hey, this number right here has 3 sig figs, whereas this number right here has 2 sig figs. So I really need to round this to 2 sig figs, which would mean this number should be 1.1 cubic meters. Okay, that's good. You've used the sig fig rules and everything's great, right? Well, here's the problem. What really matters is how much uncertainty relative to the number does each number have. So for instance, 1.09, let me do a different color here. The number 1.09, since they didn't specify an actual uncertainty, we should assume that the uncertainty is 1 in the last digit. So at 0.01 is what we call the fractional uncertainty. And if you divide 0.01 by 1.09, you will end up getting 0.009, like that. So it's on the order of 1%. Similarly, when you look at the 0.99, the uncertainty in that one is 0.01 as well. So 0.01 divided by 0.99. In that case, you get 0.01, roughly 1% again. So the fractional uncertainties going in were about 1%. If this number doesn't have a fractional uncertainty of about 1%, then I may have done something bad. So let's consider what the fractional uncertainty of this is. The fractional uncertainty would be plus or minus 1 in this digit. So I'll say 0.1 divided by 1.1. When I do that, I get 0.09, which is on the order of 9%. So I've done a great injustice, excuse me, to this problem by using significant digit rules. So significant digit rules aren't really the correct way. They're just a rule of thumb that works pretty well. You just got to watch out for when the decimal uncertainty, the fractional uncertainty of the answer differs a lot from the fractional uncertainties of the parts. Most teachers don't get you at all for that, like if you miss that, but that is something, if you're going on to be a scientist, that's something you really need to keep in mind. And in fact, you'll take a whole course on propagation of errors where you'll learn a calculus-based way of doing it. So in this case, we really shouldn't call it 1.1. We should try to call it 1.08 cubic meters. And then let's check the uncertainty in that one. The fractional uncertainty of that one is 1 in the second decimal place. So that'd be 0.01 over 1.08. When I do that division, I get 0.009, which is on the order of 1% again. So you can see by going a second decimal place for this particular problem, I got 1% uncertainty, which basically the uncertainty in this should be about the same as the biggest uncertainty of the two. So if you're multiplying two numbers or three numbers or 54 numbers, the one with the largest uncertainty should dictate roughly what the uncertainty in the answer is. If you're doing division, the same sort of thing applies. So in this case, it would not be correct to use significant digit rules. So you should always keep that in mind, just from a scientific standpoint, that really at the end of the day, the fractional uncertainties that go in should be comparable to the fractional uncertainty that comes out of a calculation. There's one more rule that you should keep in mind, and that's when, for instance, if you want to calculate the density of something, let's say density is equal to mass divided by volume, but then volume is equal to length times width times height. You have a length, you have a width, you have a height. So you're going to take a measurement, a measurement, and a measurement, and you're going to multiply those three numbers times each other. And then you're going to divide the mass by that one. You're making multiple calculations. So what you want to do is you keep at least one extra sig fig, in other words, one digit beyond the sig fig rounding spot. Always keep at least one digit more in the intermediate step. So when I multiply L times W, if it tells me to round to one decimal place, I keep at least two decimal places. And then when I multiply by H, if that tells me to round to one decimal place, I keep at least one more decimal place. So I'm now two decimal places. And you might even mark it like I did here with a little red pen, just reminding yourself, hey, this is a digit that I'm adding extra just to keep track that I'm not supposed to have that. Then you take the mass, divide it by that quantity, and use the correct significant digit rule, and then that will give you where the density should be rounded off to. But don't round, and then round again, because you end up getting a number that bears no resemblance to the answers that are in the back of your book or in the homework system. So I think that does a pretty good job for the uncertainty and sig figs. So I will call that a day.